This video illustrates how to implement binary search trees in Java. And it goes over the methods of binary search tree, which are contains or search operation, insert or add operation, remove or delete operations. And it talks about the implementation of every single operation in Java. In order to understand the binary search tree implementation that I'm going to show you in this video, you need to have a basic background on how binary trees are made using a class similar to BinaryNode. So you can watch the other video I have regarding binary nodes and binary trees in general. Binary search trees are more specific trees because they are binary trees that satisfy a property. The property is the binary search tree property, which basically says all the elements on the left subtree of every node are going to be smaller than the node, than the root, basically. And all the elements in the right subtree of every element are going to be greater than that element. So root has higher value than all the elements in the left subtree and has less value than all the values stored in the right subtree. Because of that, the binary search tree should contain values that are all comparable, right? Otherwise, we cannot test and check whether the binary search tree has the binary search tree property. Why do we call it binary search tree? Where does the search come from? It's because the search operation is pretty efficient in binary search tree. That's why we call it binary search tree. What's the complexity? I first show you that the complexity is the order of height of the tree. And then at the very end of this video, I'll show you that the average height of the binary search tree is equal to log of the number of elements in it, or I should say it's the big O of the log of the number of elements in it. And that can prove that the search operation is logarithmic in a binary search tree on average, and therefore we call it binary search tree because it has an efficient logarithmic search operation. Also, I'll show you the insert and remove operations and how they can be implemented in a logarithmic fashion, similar to the search operation. And I'll show you multiple other methods for the binary search tree. So let's begin by going over the content of binary search tree. Binary search tree is defined as a public class, which has a generic type E here, which extends comparable of any type that is a super type of E. And this class implements set ADT, set abstract data type, which basically means a data type that allows elements to be inserted, removed, and searched. And also a set is different from list because you're not allowed to store duplicates in a set, but list is allowing duplicates. And set doesn't store elements in a specific order, but list stores them in a line, in a sequence. So binary search tree implements set abstract data type. There are other implementation of sets, for example, hash tables that we'll study it later. But for now, we are focusing on binary search tree, and we'll see how binary search tree implements a set and its methods, which are add, remove, and search. So binary search tree contains the following elements. One is private inner class binary node. I'm not going to go through all the details of it. I'm just going to review it because I've done it. I've gone over all the details of BinaryNode in a different video, so we're going to save time and just briefly mention what it's inside this class. It represents a node and possibly a left child and possibly a right child. Other than this inner class, the class BST should contain some instance fields, for example, the root, which is a binary node, and also an integer size, which always shows the number of elements stored in the binary search tree. It will be incremented whenever you insert an element and will be decremented whenever you remove an element from the binary search tree. The contains method, the insert method, the remove method, these are methods that have an order of height complexity. Height is basically the height of the tree, which is defined as the length of a path from root to the deepest node in a tree. Other than these three main methods, which are the main operations that you can perform on a set, we're going to see the set method, the size method, which is a method returning size, basically a getter for the size instance field. isEmpty checks whether size is 0 or not. Clear is going to remove all the nodes in a BST. Clear is the whole set, and it gives you a set that represents the empty set. Then we have the findMin, findMax, which basically returns the minimum and maximum of a set. findHeight, which basically calculates the height. All of these methods will have an order of height complexity, similar to the contains, insert, and remove. And finally, I'll show you the toString method, which prints a set that is represented by the current binary search tree, and also it prints the actual tree in a breadth-first search traversal. In order to print the set of all elements stored in a binary search tree in order, we use the in order traversal. And then the toString method uses BFS breadth-first search traversal in order to print the actual tree containing the set. So let's get into the detail of binary search tree. Later, I will use the main class to test my binary search tree class and make sure that all of the functionalities are operating in the way that we are expecting. And then finally, I'll talk about a way to prove experimentally that the height of a binary search tree is order of log n, where n is the size of the tree. So these are the classes that I'll get to them, and I'll explain them after binary search tree class. So let's get into the details of the binary search tree class. It's called BST, stands for binary search tree. And as I said, you can have any type E stored in this binary search tree as long as E extends the comparable of super of E. And that basically means you can have an integer, you can have a double, you can have a string, you can have basically any comparable object stored in nodes of binary search tree. It stores a private binary node root. That root is basically the root of the binary search tree that stores everything. And then I have a size. The size is initialized to 0, root is initialized to null, as you may know. If you don't initialize an object, it's going to be initialized to 0. If you don't initialize an integer or a numerical value, it's going to be initialized to 0. Then I'm going to show you as the first method, I'm going to show you the contains method. Let's see why the search operation in binary search tree is so popular. What magic binary search tree does inside its search operation that makes it so popular. Let's find that. Basically, the contains is has been written in a recursive fashion. You can write it without recursion, but I'll try to teach you, how the recursion works by showing you basically almost all the methods in the binary search tree in recursion fashion. So the public contains, which basically gets a value of type E and returns a Boolean, will return the private contains method, which is going to be a recursive method, which I'm going to show you. That's called the helper method. That gets the root as its first parameter and the value that you want to search for in this second parameter. What does the private contains do? It basically looks for a value within a subtree rooted at the first parameter. So let's get into the detail of the private contains method. Here is the private contains method. Private Boolean, which returns a true or false, true if the search is successful and false otherwise, contains the name, and then it gets two parameters. One is the node, which is the root of the subtree that you're searching. Basically, it specifies the search area or the root of the subtree that is going to be the search area, and the value E, a value of type E, which you want to look for. If the node is null, that means you're basically searching in an empty tree, right? So node represents an empty subtree. So of course you cannot find a value in an empty subtree, so you basically return false. If the value is less than the element that is stored in the node, in the root of the subtree, basically I'll say if value is less than root's value, we're gonna continue the search on the left subtree, because based on the property of a binary search tree, all the elements in the left of a subtree, left of a node are going to be smaller than the node, and all the elements that are placed in the right subtree are bigger than the node. So when the value is less than the node.element, that means you cannot find it in the right subtree at all. So why not continuing the search operation only in the left side? And to do that, we're going to call the contains recursively. Now, imagine the other case. If value is greater than root's data or root's value, what's going to happen? The value you're looking for is greater than the value that is stored in the root. So again, based on the binary search tree property, it cannot be found in the left subtree. You have to only find that, you can only find that in the right subtree if it exists. And then that's why you return contains with the node.right, which is basically the right child of the current node, which becomes the root of the subtree of the current node. And then you pass the same value and try to find the value in the right subtree. And if none of these happen, if the value is neither less nor greater, it's going to be equal. So you return true. That's a successful search operation, and that means you have successfully found the value. If you want to make this a little bit more efficient, you can instead of calling compare to twice, you can basically store the comparison results in an integer, and then you just test that after that. So these are tiny adjustments, let's say, and same as here, you just say comparison result. Basically, the compare to method is a method that is defined for every comparable object. It returns a negative number if the explicit parameter, in this case value, is less than the element that you pass as an input parameter, in this case node.element, it would return a positive number if the explicit parameter is greater than implicit parameter, and it returns 0 if they are equal. The value equals node.element. So in the case that it's neither less nor greater, it's going to be 0. Therefore, you're going to return true because you have just found the value within the binary search tree rooted at node. When you call this contains method, the private contains methods with the first parameter equal to the root, it searches for the value in the whole tree that you have for your binary search tree. If it finds it, it returns true. If it doesn't find it, it returns false. And in the public contains, we're going to return the same return value that the private contains returns. That's for the search operation. So let's call this basically the search operation of set ADT. Now I'm going to do the similar explanation for the insert operation. What happens to the insert operation of binary search tree? We're going to use, again, recursion to implement this. So similar to the contains, I have two inserts. One is the public one. One is the helper recursive method, which is called within the public one. This one is private. And it gets the value that you want to insert as the second parameter, but the first parameter would be the node that will play the role of a root for the subtree that you want to insert the value in it. And the insert is going to return a node, a binary node, and the root becomes equal to that node. And then we are going to increment the size. That's going to be the whole insert operation. The contains didn't touch the size because it wasn't changing the binary search tree. It was only looking for a value in a binary search tree. So let's look at how insert private method looks like. It's going to be a recursive method, as you see here. This is the insert operation. What it does is pretty simple. First, you take care of the base case. Similar to the contains that the base case was node equals null. Here in the insert operation, the base case is if node is equal to null. If node is equal to null, that's an empty tree. So what you're going to do is you're going to return a new binary node with the value equal to the value that you want to insert. That means your tree was empty before. Now you insert the very first element into the binary tree. And guess what? That node becomes the root because it cannot go anywhere else. So that's the root. So basically you return a new binary node object with the value stored in it. And then this return value, if you remember, is going to be assigned to the root in the public insert here. So that's why we say root equals to insert. That's the main reason we have this assignment. All right, let's go forward. If you don't have the base case, which means if the binary search tree already is occupied with some elements, right? The size is not 0, it's not empty. What's going to happen? Then we don't have a base case, we have multiple recursive steps. First, you need to check whether the value that you want to insert is less than the node, the element, which means that less than the value is stored in the node, in the root, right? If the value is less, then what do? Based on the same logic that we applied for the contains and search operation, for the insert operation, we're going to do the same thing. Because this is a binary search tree and the value is less than the root, we're going to continue the insert operation in the left subtree in a recursive fashion. So we're going to say, let's do the insert on the node.left and value. Basically means let's insert the value in the left subtree, and it's going to return always the root of the updated tree. That would become the node.left. So basically we insert recursively to the left subtree. What happens if the value that you want to insert is greater than node.element. In that case, basically, we have a symmetric case similar to the previous one. The value is greater than the root. It only has to be inserted in the right subtree. So we say node.write equals insert of node.write and value. Basically, we insert recursively to the right subtree. And if none of these two happen, that means the result of comparison is 0. So that means the value already exists. So that means you're inserting a value into a binary search tree that already exists. That should fail the insert operation. Why? Because the binary search tree was a set, and set does not allow duplicate values. Therefore, you have to terminate the insert operation. And here I basically printed a statement saying that BST.insert warning value that you wanted to insert is already stored in the tree, so you cannot insert a duplicate value. So this is basically the case of the duplicate that cannot be inserted in a BST implementing set or dset ADT. And because after every insert, the public insert, I do size plus plus. In order to compensate for that increase, I have to do size minus minus, so that this minus minus cancels out the plus plus over there in the public insert, because the insertion was failed, right? If the insertion failed because you couldn't add a duplicate value. And then you can simply print this warning that, you know, the value is already there, and then you return node at the end. Node is basically the root of the current subtree that you inserted the value. I told you why you need to return it, because, you know, you either assign it here, here, or in the public insert method. Let's, before I show you the remove method, which is a little bit more complex than these two, let's quickly check why the complexity of the contains and insert method are going to be equal to the height of, or the order of height of the tree. I'm just going to draw a simple binary search tree, and I'm going to explain it using that as an example. So imagine you have a binary search tree. I'm going to write a very simple one. Let's say there's a 5 here, there's a 2 here, there's a 1 here, there's a 10 here, there's a 7 here, we have 12 here, 11 here, and 8. So imagine this binary search tree, and let's say you're looking for number 8, right? All you need to do is start from the root, which is 5, and look for and compare the values with 8. Is this equal to 8? No, 5 is less than 8. So we're going to focus only on the right subtree. We're looking for 8. So let's compare 10 with 8. Is 10 less than 8? No, it's greater than 8. So we're going to focus only on the left subtree of the right subtree, which is the one that I just highlighted. Then you compare 8 with 7. Basically, 7 is less than 8. So we're going to focus only on the right subtree of 7. And then when you look at here, you will find it and say the search was successful, right? How many comparisons should we do? In this case, we did 3 comparisons here, and at the end, you need to do another comparison. You need to say, is 8 is equal to 8? And the answer is yes, because it's equal. Then you can say, we are done searching, and we have found the value that we're looking for. How many search operations did we do? We did 4 here, 1, 2, 3, 4. in general, the number of comparisons would be equal to the height, because look, it's going to be the path that you have to traverse from root to that node. If I want to be very, very like exact and precise, I would say the number of comparisons is equal to the depth of the node that you're looking for plus 1. In this case, the depth is 3 for node 8, and the number of comparisons is 4. Right? But do we care about the exact time complexity of every contains method? No, we only look for an upper bound, right? As long as you find an upper bound for the time complexity, that's good enough. And in order to answer the upper bound, you simply say, because the contains takes the depth plus 1 number of comparisons, I will say the upper bound would be the depth of the deepest node plus 1. Depth of the deepest node is the height of the whole tree. In this case, the height of the tree is also 4 because 8 is the deepest node. And then you will say the number of operations, search operations or comparisons in a search operation would be the height plus 1, which is 3 plus 1, which is 4. But that doesn't really matter. What matters is the asymptotic notation. Asymptotically, I will say this is the order of height, right? Because it's 8 plus 1, so it's the order of height. Same for insert, because the insert follows the same logic as the contains, and basically by comparing the value that you want to insert with the root, it decides where to go to the left side, the right side. It gives you the same complexity of order of height, right? And the next operation that I'll show you, which will be remove, will be the same thing. It has a complexity of height, okay? Let me clear all the drawings and continue this with the remove operation. The next operation that I'm going to show you is the remove operation. So the remove operation of set ADT is implemented by this public remove method, which basically calls a private remove, and it calls the private one with 2 parameters. The second one is the value that you want to remove. That's basically the same parameter that you pass to a public one. And the first one is the root, and this is basically the helper recursive one. Let's get into it, and then at the end, it's going to do size minus minus, which it's obvious because you remove 1 node, so the size should be decreased by 1 unit. The remove method that is recursive and is a private helper method for the public remove has a base case and a bunch of recursive steps. Let me go over the base case, which is the simplest one. If the base case happens, that means you're trying to remove an element, remove a value from an empty subtree. Node is the root of a subtree. So if the node is null, that means you're trying to remove from an empty subtree. You can print a message saying, like, this is a BST.remove method, and this is the warning. The value that you're trying to remove doesn't even exist in the tree in the first place. So what are you doing? You cannot remove a value that doesn't exist. And then you do the size plus plus, which is going to cancel out the size minus minus that happens in the public remove, because the remove fails here, right? The removal operation fails, and then you return null. What do we return as a return value of the remove? We basically return the root of the subtree after you remove the element. If the subtree is originally empty, you basically don't touch it, so you return the same node, or you return null. You could have said, let's return node, because node is null. But so that means basically you're not doing any change in the binary tree. Why do we return the root of the subtree to from the remove private method? Because in the public method, we need it. In the public method, remove, we are basically assigning the return value of the private remove to root. And that's absolutely necessary because when you remove an element, maybe you remove the actual root. So the root will change in some cases. Therefore, you need to update the root, and that's why remove returns the updated root. Okay, so let's go with the recursive steps of remove. What happens in the recursive steps of the remove? You need to compare the value with the element stored in the root of the subtree. If it is less, if the value is less than the root, then you need to continue the remove operation in the left subtree. That's kind of obvious. Similar stories happen for the contains method, the insert method. The binary search tree has a property that forces all the elements in the left subtree to be less than the root. That's why we do this. We only continue the remove operation in the left subtree, and then this is a recursive call. If the value is greater than the node.element, then you want to continue your remove operation in the right subtree in a recursive fashion. And guess what? Anything that you see after this is used for the case where you found the node that you want to remove. So if you want to make this a little bit nicer, I can basically add a curly braces here. Actually, this already inserted. So I can add I can add curly braces here, and I say this is where we have found the node that needs to be removed, right? But why do we have too many lines of code here? Because there are several possibilities. One, which is the most complex one, is when the node that you want to remove has two children. So that seems to be a little bit complicated, because if your node has already have two children, how do you want to remove a node from it, right? Because if you just, because if your node that you want to remove has two children, and if you remove it, then you have two children that are basically orphaned. They have no parent, right? They cannot stay in the binary search tree. So how do we handle this challenge? I'll show you how to do it. And then there are three more cases. If they don't have if the node that you want to remove doesn't have two children, then it's either have a left child only or a right child only, or in the easiest case, it is a leaf, it has no child. So we're going to consider all these situations. Let's begin by the most complex one, when a node that you want to remove has two children. There are two ways to handle this situation. You can either find the minimum element, which I call it the leftmost element in the right subtree, and replace it with the element that you want to remove. So basically, you will say node that element is the leftmost. I'll tell you why the leftmost is basically findMin. The leftmost node of the right subtree. And then you continue your remove operation in the lower level in the right subtree by removing what you just replaced, which is basically node.right, right? I'm sorry, node.element. So basically, you remove the node.element that you replaced the element that you want to remove it in the right subtree. So you basically say removing the right subtree node.element. What is node.element? It's the minimum value of the right subtree. Because if you don't remove it, then you will have a duplicate, right? Because you just move the right the minimum of the right subtree into the node. you will have two of them. So you need to remove the second copy in the right subtree. Alternatively, you can do this, and these two approaches are not different. They're as good as the other. I mean, each one is as good as the other. The alternative is this: find the maximum of node.left, find the rightmost node in the left subtree, and assign it to the element stored at the root. And now, basically, you have removed the element that you wanted by replacing it by a different value, by the maximum of the left subtree. And then, in order to avoid any duplicate values, you remove the same element that replaces the removed element in the left subtree by calling the remove recursively for the node.left and node.element. And that's it. I'm just going to explain this one in a very simple, in a very simple example, and then you take care of the other one, or you think about the other one and see why both of them work as good as the other. So basically, let's say you have a root of 10. Here I have 5, here I have 7, here I have 2, here I have 4. I'm sorry, shouldn't be 4 because 10 should be less than that. So let's say 14. And then let's have one element. Let's say this is 12, right? And that's good. That's an example. Let's say you decide to remove 10, right? 10 has 2 children, so you get to this else part and say, because it has 2 children, I gotta replace it by the, if I want to use the same, code, I have to replace it by the minimum element in the right subtree. This is the right subtree. The minimum element is basically the leftmost one, this one. I have to replace it by this. So 10 will be replaced by 12. Now we have two 12s in the tree, right? So what should I do next? I should remove 12 from this subtree, because otherwise I will have two 12s. So then I will remove 12. When you want to remove 12, it's a leaf. So removing it is not going to be a big deal. Just get rid of it. Removing 10 was a big deal because when you remove 10, then you have two children, 5 and 14, with no parents, right? The alternative version is kind of simple. All you need to do is to replace 10 by 7. 7 is the left subtree's largest value, which is the maximum value in the left subtree. So you need to basically replace 10 by 7. So instead of 12, we're gonna this time replace it by 7. Sorry. Oh, gee. Sorry. Let's see. Oh. Okay. So now let's get to this one. Now this becomes 7, and now that you have two 7s, you're going to get rid of this one. And because this is a leaf, it's not going to be a big deal when you're removing it. You just get rid of it. So either you do it with the right subtree and you replace the minimum of the right subtree, or you do it with the left subtree and you replace it with the maximum of the left subtree. Both of them are equally good. Let's go ahead and finish the rest of it. In the case that the node does not have two children, then it either has one child. Let's say if it's a left child, then it's not going to be too difficult to remove the node. You basically replace the node with its left children, with its left child. So basically, you're going to return node.left, and this way you're bypassing the current node, and node.left becomes the new root for the current subtree. And then if there is a child, there is only one child in the right subtree, then you're going to return node.write. And otherwise, then if none of these happen, that means you have a leaf that you want to remove. So you don't need to do anything, just return null, because at the very end, you have removed the node that was a leaf, and the updated version of it would be an empty subtree. It was only a subtree with one node. Now it has no node, so it's going to be an empty tree, empty subtree. So you return null. And if the first two cases happened, we have to do something about the return value. That's why we return the node, which is going to be the root of the subtree. So that's basically the remove operation. It is easy to see that this one is also taking order of height. Whatever the height of the tree is, it's going to be the order of height. And that's basically it. That's the remove operation. The next operation that we're going to look at is going to be size, or I should say the next method. The next method is going to be size, isEmpty, and clear method. Let's get into the details of each one of them. The size is basically a getter for the size instance field. isEmpty compares root with null, or it can compare size with 0. Clear is going to initialize, it's going to set the root and size to their initial values. Root becomes null, size becomes 0. That means it removes everything in the tree. And then findMin and findMax are the next operators that we're gonna operations that we're gonna look at. findMin calls the helper findMin. That's a recursive method that is private, and it looks at the leftmost node and returns its value. Basically, the way it works is it starts by taking care of the base case. If the node is null, then the subtree that you're trying to find its minimum is empty, and it has no minimum, because when you have an empty set, there's no minimum. So we basically return null. Otherwise, we have the base case. We check the, otherwise we have the second base case. This was the first base case. Otherwise, we may have the second base case, which says, does the current node have any left child? If it has, then we are going to return it. Then we are going to return the element stored at the node. And otherwise, we are going to call the findMin recursively for the left subtree. What does this findMin do? Basically, it tries to find the minimum element in a binary search tree. The minimum element basically is the leftmost element. Because of the property of a binary search tree, this is going to be the minimum, because every element in the left is smaller than the element in the right. So the minimum would be in the leftmost. The maximum would be in the rightmost. So in order to find these recursively, you need to take care of two base cases first. If the node is null, empty, return null. If the node that left is null, return node.element. And otherwise, call the findMin recursively for the left subtree and keep going to the left subtree. So start from root, you go this way, this way, this way, this way, all the way to the leftmost node, then you return. That would be your final minimum value. For the max, this is the code, and basically you go to the right subtree, or every time you go to the right subtree, in every step of iteration or in every step of recursion, all the way until you reach the rightmost node, and you find the maximum. So min and max are similar. You just need to find the leftmost for min and rightmost for max. After findMin and findMax, we have findHeight, which calls root.height. Root is a binary node, therefore it has a height method. I'm going to show you the height method of binary node root later. Then it has a toString method. toString for the binary search tree begins this way. If your root is null, that means you have an empty binary search tree, so it represents a set empty. Set open curly braces shows an empty set stored in an empty tree, and then otherwise the set is not empty. So first it traverses the root in an ordered fashion. I'll show you how this works. This one returns an array list, and this array list to a string will give you the elements. We're going to get rid of the first and last element of the string representation of the array list representing all the elements, because set should be represented by curly braces. So instead of the first bracket, we use the open curly braces. And then instead of the last bracket or the last symbol, which is the close bracket, we use close curly brace. And we say this set is stored in the tree root. Root is a binary tree. This is going to call it toString method. I'll show you the toString method after this. And then that's it. That's pretty much everything that you needed to know about the binary search tree. Finally, let me get into the overview of BinaryNode. I'm not going to go through the details. That was discussed in a different video, but let's just briefly mention what it contains. We have the element data stored in every node of type E. Then we have a left and a right subtree for every node. The type would be another binary node. So every node has a left child and a right child of type binary node. Then I have a constructor that is used for leaves only. It only gets an element and then it sets the left and right child to null. Then I have another constructor that initializes the element, the left and the right child, or I should say children. That's for non-leaf node, non-leaves, or for internal nodes, I should say. Then I have height, which basically was used in getHeight of BST class. That one is done recursively. It says if there is no left and right children, return 0. That's the base case. If left is not null, if left is null, so there's only a right child. So find the right child height and add by 1, return that. If the right is null, then add 1 by left the child height. And otherwise return 1 plus the maximum of the left and right height. Then I have the size, which counts all the elements. We didn't use this in a binary search tree. We can safely remove it, but I don't want to remove it. Let's keep it here. Then we have print pre-order traversal, which prints all the elements in a binary tree in a pre-order traversal. We then use this, but that's a nice way of implementing pre-order traversal. Pre-order traversal means root, then left subtree, then right subtree. It has been done recursively, as you see. Post order visits or prints the root at the end. The rest is similar to the pre-order traversal. And print in order traversal is going to visit the element at the middle. But this is not the in order traversal that I used in the toString method of BST class. What did I use in the toString of BST class? This is the method that I used. It doesn't print it itself. It returns an array list, and basically it sorts the elements in the in order traversal fashion, which basically means in an increasingly sorted fashion. The property of the binary search tree which basically says left subtree is less than root is less than right subtree, assures that the in-order traversal is sorting all elements. Why? Because L is less than root, and root is less than triangle here. Root is less than right. So because L is less than root and root is less than right, and the in-order traversal is the left subtree, the root, and the right subtree, because this order and this order are the same, basically, the in-order traversal prints the elements in an increasing fashion. So that's the beauty of binary search tree. And guess what? Every binary tree that has a sorted in-order traversal is a binary search tree. So this is a necessary and sufficient condition for every binary tree to be a binary search tree. A binary tree is a binary search tree if and only if its in-order traversal is increasingly sorted. This is a very, very nice theorem that you can always remember. And it's very useful because when you're given a binary tree and you want to find out whether it is binary search tree or not, you can use this method, this theorem, and traverse all the nodes in order. If this gives you a sorted list, then the binary tree is a binary search tree. Otherwise, it's not. Okay, so in order to print all the elements, not print, in order to list all the elements in an array list using in-order traversal, I first created an empty list. Then the next thing I do is I will create an empty stack. I could have used the recursion, but I said maybe you will wonder what happens if you don't want to use recursion. Believe me, if you don't want to use recursion, it only makes things more difficult. In this case, I have to have a stack, and first I push this node, and then in a while loop, I will say, as long as the stack is not empty, pop one element. If it is a binary node, then push its right child, then push the element stored in the root, and then finally push the left child. The reason I first push the right, then root, then left is because when I let me show you a stack. So when I first push the right subtree, then I push, or right child, I should say, then I push the root element, the value, and then I push the left value, then the order of popping element would be left, then root, then right, which is basically the same as your in-order traverse, right? And if the all right, so if the node that if the element that you pop from the stack is not a binary node, it's not an instance of binary node, then it's going to be the element of type E. So let's add it to the array list that you have created after casting it to E, because Curry is an object. It's a superclass. You have to cast the superclass to subclass. So you need to cast it, and eventually you got to return the list. Now we gotta so this is basically the method that is used in the toString method of the BST. We have print BFS, print DFS. These methods are used to traverse the binary tree in a breadth first search or depth first search, which is basically the same as DFS. Is the same as pre-order traversal. I've already explained these in the video for binary trees. And finally, the toString method, which is going to print the binary tree in a nice fashion, same fashion that I draw it on the screen. This toString prints it in a nice fashion. When I run test it, you will find out how it looks like. And that's it. Next, I'm gonna test everything I showed you in the BST using this main class. It has a main method in it. The main method creates an empty set. It will populate the set with these numbers in the same order. Basically, in this for loop, I will say, first of all, this set is going to store integer, because I said BST of integer. Right? An integer is comparable, so everything is fine. This for loop insert all of these values one by one using the insert operation. Before inserting, it checks whether they are already there using the contains method. And if they aren't, if they are already there, it doesn't print the insert message. But if they are not there, that means it's not a duplicate insertion. Then it prints, let's insert this value, and the result will be the set. So every time it adds a new value, it prints the set, which basically calls a toString method of the BST, which I showed you before. It draws the whole tree after it lists all the elements in the set. Then I print the maximum, the minimum, and the height of the tree. And then in another for loop, I begin to remove 4 elements. 3 of the 4 are going to be removed successfully. The last one is not going to be successful because it is a non-existent value, so it doesn't exist. What do you want to remove? It will give you a warning, and that's it. So let's run it and see the outcome. So look at the order of inserting elements. Let's begin by move up. Let's begin by the first insertion. We insert 12, and the result will be this. You have a set with only 12 in it, and that stores this tree. Tree is only one node, and that's 12, and that's it. 12 is the root, and that's it. Then I will insert 8. 8 is less than 12, so it will be placed in the left subtree. So we have 12 on the root, left child is 8. Set would be 8 and 12. Then I insert 6. 6 would be less than 8, so it would be the left child of 12, then it would be left child of 8, and it's going to be stored here. 10 is going to be less than root, which is 12, but greater than the left child, so it becomes the right child of the left child of the root. The set looks like this, the tree looks like this. Then I insert 60. 60 will be the right child of the root because it's greater than it. 9 will be less than 12, greater than 8, less than 10. So it's going to be the left child of 10. 11 would be the right child of 10. As you see, after I insert everything, I build every element, I print out the actual tree to show you the difference or the update. Then I will insert 100. 100 will be the right child of the 12 because it's greater than 12 and 60. So it should be stored in the rightmost location. Then I have 50. 50 will be the left child of 60. 7 would be the right child of 6. Again, you're going to start from the root. 7 is less than this, greater than this, so it should be here. Then I will have 60, but 60 is already stored in the tree. As you see, 60 is here, so it says you can't insert 60 anymore because we cannot accept duplicates. Then we insert 4. 4 is going to be the left child of 6 because it's smaller than 6. And then 3 would be the left child of 4 because it's smaller than 4. Then we insert 55. 55 would be the right child of 50. Then we insert 5. 5 would be the right child of 4. Then we insert 4 again, but 4 exists already. So you get this warning message. Then you're going to insert 22. When you insert 22, what do you get? You have to insert it in the left subtree of 50. It's greater than 12, less than 60, less than 50. So it's going to be here. Then you're going to print. So this is the whole tree after inserting all those values. Then you're going to print the maximum value. I mean, that's what I did. Here I printed the max value, the min value, the height. So when I print the max value, I will see 100. 100 is basically the rightmost node. As I showed you, always rightmost node would be the maximum. The leftmost node would be this one, which is 3. And the height would be 4 because there are 4 levels. 0, 1, 2, 3, and then these are the deepest nodes 4. The height is 4, and then I start removing 12. You don't see 12 in this anymore, and 12 is the root. So when you remove the root, it has 2 children. If you remember, we got to replace 12 with the leftmost node in the right subtree, which is 22. So 22 becomes the new root, and then 22 is going to be missing in the right subtree. There's no 22 anymore. 22 was the left child of 50. Now 50 has no left child. 22 is here now, is the root, the new root, after removing 12. Then if you remove 50, that's an example of removing a node with only 1 child. 50 has only 1 child. When you remove it, the child will replace the parent. So 55 comes up, 50 will be gone. And then when you remove 55, well, 55 is a leaf. So when you remove it, nothing happens. Because 55 is missing and that's it, right? And then when you try to remove 23, it says it doesn't exist in the tree. What do you want to do? So that's pretty much the main class that was testing binary search tree. The last part of this video focuses on proving experimentally that the height of a binary search tree is on average the order of log of n, where n is the size of the tree. Let's find out how this is possible. When I say log, I mean log base 2. But it doesn't really matter because when you say big O of log n, it can be log of any constant, right? The base can be any value because log base 2 is big O of log base 20. I should say big theta. Big theta of log base 20 is big theta of log base 2 billion. They are all the same base. They all are going to be the same growth rates. Let's see how we can prove the average height is logarithmic. I will implement a sequence of 10 experiments. If you want to get a more precise result, instead of 10, you can say 100. And you don't need more than 100 experiments. And then this is what I do in the main method. I can say, let's create a random generator. Let's create an empty set, empty binary search tree. Then I will have a for loop for every n from 5, 500, 50,000. This is 5 million and this is 50 million. I do this. I will say, let's have a for loop. Let's do this 100 times for round 0 to round 99. Do the following. First, clear the set. Whatever the data was stored before in the set, let's clear it, remove everything. Then in a for loop, as long as the set size is not equal to n, generate a random value, random integer using random.nextInt, and insert it into the set, right? You don't need this if, and that's it. After you inserted n elements or n random integer into the set, then call the findHeight to calculate the height and use that to find the average height. Average height is a double which will be initialized to 0 every time. It's going to be added by findHeight over the number of experiment. That's basically a tricky way of finding the average. You don't need to be worried about the math behind it. But anyways, at the end, I'm going to print out the height of a binary search tree with certain node. N node would be whatever. n it grows exponentially. First is 5, then it's multiplied by 100, 500, then multiplied by another 100, 50,000, no, multiplied by 500 again, 5 million, and then multiplied by 10, get to 50 million. And that's it. So let's run it. I don't want to show you the whole running time. It's going to take you a long time to see the output. Sorry, let me stop this. I have to first do an adjustment. I'm gonna make my BST is verbose now. I have to make it silent because it prints too many things, and all of it is because of what? Because of the insert print statement, which is all the way on the top. Here is the problem maker. So let's run it now. As you see, it says the average binary search tree, the average height of binary search tree with 5 nodes is this much, with 500 nodes is this much, with 50,000 nodes is this much, and then for 5 million and for 50 million, it takes a long time. But I've already done the experiment offline, so let me show it to you. It's going to be this one. Yes. So as you see, it shows you the average height. It's going to be 2.7 for 5 nodes, 18.3 for 500, 37 for 50,000, 55.2 for 5 million, and for 50 million, it's 63.8. And you know what this shows you? It shows you that when growing the size, which is n, exponentially, the height increases linearly. What does that mean? That means when growing the size linearly, the height should increase logarithmically. I can basically show you that all of these heights are going to be a constant times the log of n. So this is basically equal to approximately, I don't want to say equal to, I will say approximately equal to. So, but I don't have an approximation. I'll just say equal. That would be basically about 2 times log of 5 base 2. Approximately. It's not going to be exact. You do the math at home, you know, you say, oh, you lied, but it's an approximation. You do it at 500, you get the same 18.37. If you do this for 50,000, similar. You do it for 5 million, you get 55 something. It's 50 something. And if you do it for 50 million, you're gonna get to there to a number around this, right? So that shows you that n is gonna be order of h. Now, what's the point of this? Why did we care too much about? I'm sorry, my bad. The conclusion is this: height is equal to order of log of n. Right? Now, why did we care about the order of height? Because as I showed you before in the binary search tree, a lot of operations like contains, insert, remove are all order of height. Now that I proved that height is the order of log n on average, so you can say contains, insert, remove, findMin, findMax, findHeight, These all methods are logarithmic methods, the order of log of n, where n is the size of the tree, which is the number of elements stored in the binary search tree. The toString method, or the printing in order, these are linear functions. These are order of n, not height. So that's pretty much it. Thank you for watching the video.